sun is clearly doing an experiment, and those of us who work in the interplanetary medium are seeing the results of it as well. And so Randy and Joe and the co-organizers have asked me to tell you about the interplanetary side of the story. So the familiar sunspots and their associated time series and spatial patterns, the butterfly diagrams are only the tip of the iceberg, of course. This is only the superficial part of the solar cycle. We are progressing in our fields to the point where there are solar dynamo models, such as this one from the Goddard Scientific Visualization Center, of a new model that's out that uses helioseismic data to model the interior convection of the sun and wind up toroidal fields and produce poloidal fields that poke out of the surface and produce the surface fields. So we are getting better all the time in our ability to understand the origins of what we're seeing on the surface. But magnetograms reveal the details that we care about ultimately in the interplanetary medium. And what we have to remember is that the sunspots and all those things we count and track back in time are not the whole story. That if you look at a magnetogram during solar maximum, for example, on the left, you see that there are magnetic fields that are concentrated that are not appearing in the white light or continuum images at the top. The images on the right, by the way, are recent images before the new appearance of the sunspots. We understand where these active regions come from to some degree. The flux from the dynamo activity seems to emerge in concentrated regions on the sun. It erupts from the subsurface. The left-hand images show the magnetograms and white light images, as well as a couple of filtered wavelengths, and a simulation of an erupting, emerging active region from below the photosphere is illustrated on the right. Now, these emerged active region fields disperse and decay on the surface of the sun on timescales of days to months. The current understanding is that the surviving flux that's swept to the poles determines the largest scale fields in the corona that affect the interplanetary medium and also are responsible for the polarity reversals that we see. Better, thank you. The helioseismology and solar surface observations together have revealed the responsible motions for these activities. We have the differential rotation on the left. In the middle, the meridional circulation in the convection zone is a key player, and then there's a shallow convection pattern due to granulation and supergranulation that's causing a diffusive kind of motion of that surface field as well. And by the way, that's instrumental in bringing positive and negative fields that have emerged together and doing cancellation and removal of flux from the surface. Now, what we end up with is a solar field that combines large and small scales. There's the largest, the dipolar contribution, illustrated on the right, and the smaller scales from the active regions can make many high orders of spherical harmonic contribution. And what we end up with are maps of this kind of the global field of the sun, which are really what we care about in the interplanetary medium. These are the boundary conditions on the corona, and these are the things that map out, and these are the things that cause us to have positive and negative fields in the heliosphere and open and closed field regions that are rising from certain portions of the sun. And you've probably all seen this nice sequence of Yoko images in soft X-rays and the corresponding magnetograms that just reinforce the fact that all processes that we know about on the sun are affected by the pattern and presence of these magnetic fields and their cycle. It was already said earlier that the overall field of the sun right now in this cycle is weaker than in the previous cycles for which we have measurements. Shown here are some Wilcox Solar Observatory data. On the top plot, the sine flux in a longitude averaged way for the previous 3 cycles, and on the bottom, the unsigned flux. And what you see is that the butterfly on the lower far right has far fewer contours of field than the other two. And so we don't only have to worry about mapping out weak polar fields here. We have to worry about those occasions where we're mapping fields out from the lower latitudes as well. And part of the story also is the multipolar content of the current field. The dipolar contribution of the three cycles is shown on the top, quadrupolar and higher order harmonic on the bottom. And what is happening is that the dipolar contribution is decreased to a greater extent relative to the other higher order harmonics this cycle than in previous cycles. So we have a solar field whose largest scales are dominated by somewhat higher order terms than previously. Now, what is the consequence? Our traditional picture of the solar wind is this very nice dipolar solar wind where the solar wind is coming out of the polar regions, polar coronal holes, dark coronal holes, as in this previous cycle image, and filling the heliosphere. But this time around, we've had plenty of very large, low-latitude, open field regions on the sun, coronal holes. These dark regions are where the solar wind has been emanating from, especially in the 2007-2008 timeframe. And this has affected what the heliosphere has experienced. When we looked at the statistics of the interplanetary contributions to the from this ecliptic plane field using the Omni data set at the Goddard Space Flight Center, statistically speaking, what we have here in the middle are statistics of solar wind density and velocity. The density, which shows a much lower average density in the red histogram than in the previous minimum in the black histogram from the periods you see at the top. The velocity histogram is not so much different. It's a typical declining phase solar minimum velocity histogram. And in the bottom are the magnetic field statistics, which show correspondingly a weaker magnetic field, as has been discussed before. So we do have a situation where, in spite of these low latitude coronal holes, we're mapping out weaker magnetic fields, but perhaps this is because the weak field extends throughout the surface of the sun. And Ulysses has found these weak fields and low densities at high latitudes that similarly suggest the general weakness of the solar wind that's mapping out. But we have some questions related to how that weakness is originating. Now, the solar wind density and interplanetary field both depend in part on the coronal hole areas, not only the generation mechanism. So one question is the amount of photospheric flux and also solar wind flux that's mapping out having to do with the changes in coronal hole areas as opposed to changes in the actual generation mechanism. And we can test things with the knowledge we have now. One of the models we have to use is potential field source surface model. It's not perfect, but it's simple. It allows us to evaluate for any field pattern on the sun the open and closed field regions, and therefore presumably the area of these open field foot points through which the solar wind is reaching us. And we've been able to, with these potential field source surface models, these are based on Gong magnetograms, and you can find them on the Gong website on a regular basis if you wonder where today's solar wind is coming from. You can see that on the far right, the sources of ecliptic wind from this period where we've had the low latitude coronal holes is decidedly low and mid latitude. It's not coming from the polar regions. So I wish people would expunge from textbooks all these purely dipolar solar wind pictures, because they're not generally applicable. There are times like the present where the solar wind really has low latitude sources that are dominating the ecliptic, dominating our solar activity, dominating what we're measuring upstream of the Earth. Another thing we found was that we had to move the source surface of this potential field source surface model closer to the sun. In the past, it was just presumed to be fixed at 2.5 solar radii, and one would be able to get a good picture of the pattern of dark and light in these extreme ultraviolet pictures that show the footprints of the open field regions. But as you see in the circled images here and on the upper right and lower left. The better match comes from a larger coronal hole producing smaller source surface. Here we went to the extreme of 1.5 solar radii as opposed to 2.5 solar radii. So the sun is not only adjusting where the open field regions are, but it's adjusting the height of the last closed field line as well. And that has to do with the weakness of the solar field as well. In the end, when we compute over the last 2 solar minima what the percent of coronal hole area on the sun is using these 2 different source surface distances, the top curve shows the fraction of the global sun that is open based on the potential field model for the 2 source surface heights, the black being the larger source surface and the red being the smaller source surface. And in theory, we think we're switching from the black model in the first shaded band on the left with the previous minimum to the red model on the right in this minimum. And so we are indeed having a greater area of open flux here in spite of the fact that we might have a smaller coronal hole area, smaller polar coronal hole area. Sorry. And this is what happens to us if we evaluate the flux that's mapping out when we have this changing source surface. In the previous minimum, we have the value of the magnetic field or the total flux that's shown within the black shaded region on the second panel. And on the right, we would jump to the red curve. And so we still have a diminishment of the interplanetary flux, but it's less of a diminishment than it would be if the solar source surface had stayed the same location. So the sun has somewhat compensated for the fact that it's producing this weaker field as far as the interplanetary field is concerned by giving us a larger area of open field region and therefore more interplanetary flux than we would have if it had its old behavior in terms of the last closed field line and the height of the source surface. So we can't just assume that the sun is behaving the same in every minimum, and this minimum has taught us that we should look closely with all the tools we have to understand the way field is mapping out and where it's mapping out from, rather than assuming it's as it was in the past. And here I'm just iterating on the fact that the source surface compensation is there. So in spite of all of these calculations and assumptions and trying to understand where the interplanetary field is coming from this cycle and how it's being controlled by what's happening on the sun, the fact of the matter is it's still going down. And even though we potentially have these little flurries of activity, so far it hasn't been enough to turn things around. The mechanisms that are causing flux to decay on the surface, to shift around, are still making a net loss of flux and interplanetary flux. And you can see on the geomagnetic index plot on the lower right from the NOAA Space Weather Prediction Center that it looks like it's not heading back up in any realizable or arguable way, in spite of the fact that we have had these recent flurries of activity. So I think that we do think that there is a solar cycle, but we don't know how low this one will go. And so those of you who have models that are based on interplanetary field magnitudes, magnetospheric models, ionospheric models, might want to start playing with 1 nanotesla interplanetary fields to see how they change their behavior. It might be a very interesting experiment that would be predictive at the same time. I don't think we fully appreciate the importance of coupling to all these systems that the interplanetary field plays and how much a change of that magnitude, how much difference that will make. So I think that's about it. And of course, the galactic cosmic ray flux will keep going up, and perhaps the question of whether cloud cover is altered at all might be revealed in the end. So the bottom lines are here, and they essentially repeat what I say. I don't know if I have time to read through these, The inference of interplanetary conditions from solar observations requires some care in considering how different features of the photosphere map out. There are coronal hole area considerations. There are considerations of the locations of the coronal holes and where they are mapping to on the surface and what kind of flux is contained in those open field regions. And we should bring all this knowledge to bear on this current solar minimum. The solar minimum is affected by the larger relative contribution of higher order spherical harmonics to the large-scale coronal field and by an apparently smaller source surface for the solar wind, which partially counteracts the effect of the weaker flux. The causes of the reduced surface magnetic field from the dynamo are still to be determined. The dynamo might be happily cranking away flux in the solar interior, and maybe the delivery system that's bringing it up to where we can see it and where it affects the corona is what's changing. I don't think that we understand the generation of the solar field sufficiently well and the internal activity of the sun sufficiently well yet to be able to make that distinction. And I'm hoping that missions like SDO might bring to bear on this question. And it's a very timely experiment if we can get it up there and working. So thank you, and stay tuned. We might have a session on the effect of 1 nanotesla fields on solar planetary interactions on the next union session. Thanks. The co-organizers have asked me to tell you about the interplanetary side of the story. So the familiar sunspots and their associated time series and spatial patterns, the butterfly diagrams are only the tip of the iceberg, of course. This is only the superficial part of the solar cycle. We are progressing in our fields to the point where there are solar dynamo models, such as this one from the Goddard Scientific Visualization Center, of a new model that's out that uses helioseismic data to model the interior convection of the sun and wind up toroidal fields and produce poloidal fields that poke out of the surface and produce the surface fields. So we are getting better all the time in our ability to understand the origins of what we're seeing on the surface. But magnetograms reveal the details that we care about ultimately in the interplanetary medium. And what we have to remember is that the sunspots and all those things we count the sun is clearly doing an experiment, and those of us who work in the interplanetary medium are seeing the results of it as well. And so Randy and Joe and track back in time are not the whole story. That if you look at a magnetogram during solar maximum, for example, on the left, you see that there are magnetic fields that are concentrated that are not appearing in the white light or continuum images at the top. The images on the right, by the way, are recent images before the new appearance of the sunspots for contrast. We understand where these active regions come from to some degree. The flux from the dynamo activity seems to emerge in concentrated regions on the sun. It erupts from the subsurface. The left-hand images show the magnetograms and white light images, as well as a couple of filtered wavelengths, and a simulation of an erupting, emerging active region from below the photosphere is illustrated on the right. Now, these emerged active region fields disperse and decay on the surface of the sun on timescales of days to months. The current understanding is that